In our last bit, we're going to do solubility, which is going to be all related to KSP. So back in 1211, you would have done some experiments where you had a bunch of soluble compounds and then you mixed them together and you saw whether a precipitate formed, and you made a little chart that said, and this is soluble versus insoluble, and you memorized that list of solubility rules. And now we've got a more sophisticated tool to be able to deal with that. And so remember, we've got this idea of equilibrium that we can work with now. So calcium fluoride is insoluble, right? It's going to form a precipitate, but that doesn't mean it's not in dynamic equilibrium with the ionic phase, right? Because it's calcium fluoride solid, and it's a reversible reaction where I'm forming calcium 2 plus and 2 fluoride ions. And I can set up an equilibrium expression, products over reactants, for that, where I've got calcium 2 plus and fluoride squared and over 1. That's our reactants because this guy's a solid. And because we're looking at a specific K, that's the solubility here, we're going to call this guy KSP, just like we called KW, the water ionization dissociation constant, or Ka if we're looking at acids, or Kb if we're looking at base dissociation. We're going to call this KSP because we're looking at solubility, and it's SP because it's solubility product, right? So it's solubility and product because we're multiplying these guys together. So all ionic compounds dissolve in water to some degree. However, many compounds have a really low solubility, and we're going to call those insoluble. Concepts of equilibrium can be applied to salts dissolving, and using the equilibrium constant, KSP, their relative solubilities in water can be determined. So the equilibrium constant for the dissociation of a solid salt into its aqueous ions is called the solubility product, KSP. So for an ionic solid M to the N XM, the dissociation reaction is that my solid breaks up into N moles of M plus and M moles of N plus. So this is your drop and swap that happens here. And the solubility is going to be K is equal to M plus M to the N and X to the N minus M to the nth power. So you're just doing products over reactants again, like we would with any solubility. So for example, the dissociation reaction for lead chloride, PbCl2, lead chloride solid, dissociates into lead 2 plus aqueous and 2Cl minus aqueous. And our KSP is the concentration of lead 2 plus times the concentration of chloride ions squared. All right. So we can look at the solubility of lead chromate. Right, so the solubility of lead chromate is 4.5 times 10 to the minus 5 grams per liter. And that tells me how much I get in solution. Calculate the KSP. Well, this solubility is in grams per liter. When I'm looking at my equilibrium expressions K, those are in moles per liter. So the first thing I've got to do is convert my solubility from grams into solubility in moles per liter. So I'm going to take my 4.5 times 10 to the minus 5 grams per liter, divide by the molar mass, and I'm going to end up with 4.7 times 10 to the minus 7 molar. All right, then I can, use my equilibrium, so I'm a balanced chemical equation. You use my KSP value, so KSP is going to be S squared. Well, that's the concentration of each of these two things. To find K, I just plug in my equilibrium value. So this solubility is my equilibrium value. Plug it into my expression for K and solve, right? So just like you would do for any other old equilibrium problem where you're given the equilibrium concentration, so you can calculate K. Right? Obviously, different things are going to have different KSPs depending on what they are. So barium fluoride is different from barium sulfate by about 5 orders of magnitude. Calcium fluoride is different from barium fluoride. Right? So different compounds are going to have different KSP values. Now, there are two terms that we need to straighten out. One is solubility. Solubility is the amount of solute that will dissolve in a given amount of solution at a particular temperature. This guy is usually given in grams per something. So it's oftentimes grams per 100 milliliters, right? Check your units, right? So solubility with a big capital S here, right? That is oftentimes referring to something in grams per volume. Right, so that's often grams per 100 milliliters or grams per liter. It could be some. So solubility oftentimes refers to grams. Most of the time in a chemistry class, we're going to say solubility and we're going to assume that we're talking about molar solubility. I don't want you to assume that. I want you to check and be careful about this because molar solubility is the number of moles of solute that will dissolve in a liter of solution. What's the difference? Well, this one is in moles, and that's going to be in moles per liter. Molarity, we're very comfortable with that. We like working with molarity as chemistry people, but regular solubility is what you can actually measure in a lab. So somebody in an environmental lab or somebody in industry might have solubility in grams because you can measure grams easily. You cannot directly measure moles, right? So molar solubility is the molarity of the dissolved solute in a saturated solution. So for the general reaction, M sub n, X sub m solid goes to n m to the m plus aqueous plus m x to the n minus aqueous. Our molar solubility is going to be like this. You can set up a regular old ice table. You can work through it. It's going to be the same basic thing each time, just like we saw as the same basic problem each time with the acids or the bases, where we had a Ka and it was find the pH of a weak acid, you're finding the H plus concentration of a weak acid. Here we're looking for the solubility of one of these things, either the M or the N. Oftentimes you're more concerned about the M than the X guy. You're more concerned about the cation because that's going to be like the metal thing, right? So like lead hydroxide, right? You want to kind of know about the lead, don't care as much about the hydroxide part. So I made you a little hand. This is a convenient equation to do that. Personally, I would just set up an ice table each time. If you want, here's a handy little table. If I got two things, my solubility S of either of these is just going to be the square root of KSP. If I've got three things like FPBCl2 or FeOH2, it's going to be the cubed root of KSP over 4. If it's four things, it's going to come out like this. So it kind of depends on what you're trying to solve for. Molar solubility is related to KSP. The KSP values cannot always be compared, right? So if I take lead chloride, the solubility of lead chloride, and the solubility of Ag chloride, right? I can't just compare them directly and say which one is more soluble because they've got different stoichiometry, right? So one of them is going to be the square root of KSP, there's going to be the cubed root of KSP over 4. So I can't just take AgCl and HGI. Right? I can't, well, I can take HgCl and HGI, right? Because they're the same, they're going to break up into the same number of things. Or I can take lead chloride and iron hydroxide, but I can't just look at the KSP between AgCl and PbCl2 and say which one is more soluble, right? Because they're going to have different solubility constants. And that's actually a pretty good example because AgCl has a larger value than PbCl, but PbCl is actually more soluble than AgCl. So to convert solubility to KSP, solubility needs to be converted into molar solubility via the molar mass, and molar solubility is converted into the molar concentration of ions at equilibrium. So it's an equilibrium calculation, and KSP is the product of the equilibrium concentration of the ions. So you take your molar solubility of your compound in grams per liter, molar solubility of the compound in moles per liter. So this is a mass to moles conversion using the molar mass. That gives you the molar concentration of the ions. You can then find KSP. Right. So let's look at an example where we've got tin sulfide. So tin sulfide solid will dissociate into tin 2 plus and S2 minus. I can set up an ice table. Don't care about the tin sulfide itself. I'm going to start off with no tin 2 plus and no sulfur minus, sulfur 2 minus. I'm going to gain a little bit of each of these, right? I would lose a little bit over here, but it's not shown up in the equilibrium, right? Equilibrium concentration is going to be S and S. Just use an S instead of X, right? I could have used X, could have used Y. Right, my KSP is going to be the concentration of tin 2 plus times the concentration of S2 minus, which is equal to 1 times 10 to the minus 26. I'm trying to solve for S. So I get 1 times 10 to the minus 26. K is equal to S squared. I want S by itself. I'm going to take the square root of that, and I'm going to end up with 1 times 10 to the minus 13 molar. So that I've got 1 times 10 to the 13 moles per liter of tin 2 plus and 1 times 10 to the 13 moles per liter of sulfur 2 plus. If I want the solubility, right, I need to convert that into grams per liter. So I'm going to go 1 times 10 to the minus 13 moles per liter times the molar mass, 150.77 grams per mole, equals 1.5 times 10 to the minus 11 grams per liter. We can do another one, calculate the molar solubility of magnesium fluoride in water. Here, the same basic setup. We're skipping straight to the equilibrium step. I've got X and 2X over here, right, because I'm making twice as much fluorine. So KSP is 7.4 times 10 to the minus 11, which is mg times F squared. So x times 2x squared. So I got 4x cubed is equal to 7.4 times 10 to the minus 11. Divide by 4, take the cubed root. X is the concentration of magnesium, so the molar solubility is 2.6 times 10 to the minus 4 molar. Right. Here's another example where we've got lead chloride. So lead chloride solid is going to dissociate into lead 2 plus and 2 Cl minuses. The setup is exactly the same as we did back here for the magnesium fluoride, except we've got lead chloride. It's going to dissociate into 1 and 2 things. So I've got S and 2S. So at equilibrium, it's S and 2S, which means my K expression is going to be lead 2 plus times chloride ion minus squared. So I get S times 2S squared is equal to 4S cubed. S is the cubed root of KSP over 4, which is 1.4 times 10 to the minus 2 molar, right? And so that's not insignificant, right? Practices calculate the molar solubility of iron hydroxide in water. One of the useful things about this is that we can predict whether or not something is going to precipitate. So let's say, for example, I can compare the reaction quotient Q to the KSP. So for an example, I've got the reaction XMN goes to M and X. Q is going to be set up the same way as KSP would be. So I've got the concentration of M times X to the N. I is going to designate the initial concentrations. If Q is less than K, no precipitate will form. If Q is greater than K, it's going to precipitate until Q is equal to K. Right? So in other words, if Q is bigger than K, I've got more product than K would suggest. I need to backform reactants. I need to decrease the concentration here, right, and form the reactant, which is the solid. Right? So it's going to precipitate and lower this concentration until Q is equal to K. Right. I can do stuff with a common ion. So if I add a soluble salt that contains one of the ions of the insoluble salt, it's going to decrease the solubility of that insoluble salt. So, for example, the addition of sodium chloride to the solubility equilibrium of lead chloride, it's going to decrease the solubility of lead chloride. So if I add stuff in here, which way is the equilibrium going to go? It's going to go this way. If it goes this way, I've decreased the amount of lead that I've put into solution. And that's one way that you can help remediate wastewater, right? As I'm going to add some common ion, I'm going to precipitate this lead chloride out as a solid, decrease the amount of lead. Right? Addition of Cl minus shifts the equilibrium to the left. Right? Same thing if I added extra Pb, it would shift it to the left. Addition of the common ion just reduces the solubility. As with other equilibria, the solution precipitation equilibria was subject to Le Chatelier's principle. If we dissolve sodium fluoride in a saturated solution of calcium fluoride, the calcium fluoride will precipitate. So we add in some fluoride minus, shifts it to the left. The decrease in solubility is called, with a salt, is called the common ion effect. And where it starts to get interesting is when some of these things, like this fluoride, can also be acid bases. So, or if I've got something that's got an OH in it, right? So it's sensitive to the pH of the solution. Right? So at high pH, equilibrium is going to shift to the left because I've got extra OH minus. At low pH, H3O is going to react with the OH minus and remove some of this. Equilibrium is going to shift to the right. So I can have some pH sensitivity in my solubility because of Le Chatelier's principle and because of the common ion effect.